Good day, everyone. Our discussion for today is about handout number 2, which is all about atoms, molecules, and ions. But before we discuss equations, chemical reactions, or material properties, we first need to understand the smallest building blocks of matter. I want you to look around you. Look at your laptop or your cell phone, and even the concrete wall surrounding you. Although these objects appear very different, they all have one thing in common. They are made of matter. So, as what has been discussed in our previous handout, matter is anything that has mass and occupies space. So, as future mechanical engineers, everything that you will design, manufacture, or analyze will involve matter. So, whether you are designing engines, pressure vessels, or renewable energy systems, the success of your design depends on understanding the materials from which they are made. But what makes steel strong? Why is aluminum lightweight? Why does rubber stretch while glass breaks easily? So, the answers to all these questions begin at the atomic level. Before we discuss these three important laws, let me tell you a true story. Imagine living in France during the late 1700s. At that time, many people still believed that when something burned, it released an invisible substance called phlogiston. According to this theory, materials became lighter because they lost this mysterious substance during burning. But there was one scientist who wasn't convinced. His name was Antoine Lavoisier. Unlike many scientists of his time, Lavoisier didn't rely on assumptions. He believed in something we still practice in engineering today. If you can measure it, you can understand it. So he did something simple but revolutionary. So he carefully weighed every substance before and after a chemical reaction. For example, he heated mercury inside a sealed container and measured the masses of the mercury, the air, and the product that formed. To his surprise, he found that although the substances has changed, the total mass remained exactly the same. So nothing was lost, nothing was magically created, matter simply changed form. So this observation completely disproved the phlogiston theory and eventually became what we now know as the law of conservation of mass. This law states that matter cannot be created or destroyed. During a chemical reaction, the substances may change into new substances, but the total mass remains constant. Let's look at the illustration. We have a closed reaction vessel placed on a balance. Before the reaction begins, the system has an input mass of 1 kilogram. Inside the vessel, the particles rearrange themselves during the chemical reaction. Notice that after the reaction, the output mass is still 1 kilogram. The substances inside have changed, but the total mass remains exactly the same. This gives us the fundamental equation shown below. Input mass is equal to output mass, or simply, total mass before a chemical reaction equals the total mass after the reaction. This law tells us that matter is neither created nor destroyed. Instead, atoms are simply rearranged into new combinations. This principle is extremely important in engineering. So when designing industrial systems, we always account for every kilogram of material entering and leaving a process. If the numbers don't balance, something has been overlooked. The second law is the law of definite composition, sometimes called the law of constant composition. Notice the circular diagram. The compound is made up of 75% of element A and 25% of element B. These percentages never change. No matter how much of the compound you prepare, whether 1 gram, 1 kilogram, or 1000 kilograms, the proportion remains exactly the same. That is why the label below says fixed mass fractions. Every pure compound always contains the same elements in exactly the same proportion by mass. One excellent example is water. Regardless of where water comes from, pure water always contains approximately 11% hydrogen and 89% oxygen by mass. This law is one of the reasons manufacturers can maintain product quality. So if the composition changes, the substance is no longer the same pure compound. The third law is the law of multiple proportions. This law applies when two elements combine to form more than one compound. Let's look at a graph. As we move from compound 1 to compound 2 to compound 3, the amount of one element increases in simple steps. Notice that these increases are not random. Instead, they follow small whole number ratios. That is why the slide uses the phrase discrete multipliers. Nature doesn't combine atoms using random fractions. Atoms combine in simple whole number relationships. A good example is carbon and oxygen. Carbon can combine with one oxygen atom to form carbon monoxide, or with two oxygen atoms to form carbon dioxide. Only the ratio changes, but the resulting compounds have completely different properties. This observation strongly suggested that matter must consist of tiny particles that combine in fixed whole numbers. These particles are what we now call atoms. So, what do these three laws have in common? The law of conservation of mass tells us that matter is never lost. The law of definite composition tells us that every pure compound has a constant composition. And the law of multiple proportions tells us that atoms combine in simple whole number ratios. Together, these observations provided convincing evidence that matter is not continuous but is made up of tiny discrete particles. These observations eventually led scientists to propose the atomic theory. Now that we understand the law of definite composition, let's examine one of the best examples of this law, water. Notice the title of this slide, System Benchmark, the constant composition of water. I purposely use the phrase system benchmark because in engineering, a benchmark is a standard or reference that we use for comparison. Pure water is one of the best chemical benchmarks because its composition never changes. Whether the water comes from rain, rivers, oceans, underground, glaciers, or a laboratory, once it is purified into pure water, it will always contain hydrogen and oxygen in exactly the same proportion by mass. This is exactly what the law of definite composition tells us. Suppose we have 20 grams of pure water. This entire sample represents one whole part by mass or 100% of the compound. Our goal is to determine how much of this mass comes from hydrogen and how much comes from oxygen. So let's begin with hydrogen. According to the diagram, out of the total 20 grams of water, only 2.2 grams is hydrogen. The first quantity we calculate is called the mass fraction. The equation is mass fraction is equal to mass of element over the mass of compound. Now let's substitute the known values. For hydrogen, the mass fraction becomes 2.2 grams over 20 grams, and that is equal to 0.11. So what does that mean? It means that for every one whole part of water, only 0.11 part is hydrogen. So most people understand percentages more easily than decimal fractions. If we convert the mass fraction into percent, therefore, hydrogen contributes 11% of the total mass of water. So I want to emphasize this. So this does not mean water is composed of 11 hydrogen atoms. We are talking about 11% of the total mass, not the number of atoms. Now let's perform exactly the same calculations for oxygen. Again, mass fraction equals mass of element divided by mass of compound. Now let's calculate. For oxygen, we have 17.8 grams over 20 grams. So the mass fraction of oxygen is equal to 0.89. Again, this means oxygen contributes 0.89 part out of the one whole part. So converting this to percentage, we have 89% of the total mass is oxygen. So let's verify our results. Hydrogen 11% plus oxygen 89% equals 100%. Likewise, 2.2 grams plus 17.8 grams equals 20 grams. Everything balances perfectly. So this confirms that our calculations are correct. So far, we have determined the percentage composition of water, but engineers often ask another question. If I know the mass fraction of an element, can I calculate how much of that element is present in a much larger sample? The answer is yes. That leads us to the next slide, where we develop a general equation that allows engineers to calculate the mass of an element in any amount of a compound. Here's the problem. Pitchblende is the most commercially important compound of uranium. Analysis shows that 84.2 grams of pitchblende contains 71.4 grams of uranium, with oxygen as the only other element. The question is, how many grams of uranium can be obtained from 102 kilograms of pitchblende? So before solving, let's identify the important information. First, we identify the given data. We know that 84.2 grams of pitchblende contains 71.4 grams of uranium. And the problem is asking us to determine the number of grams of uranium contained in 102 kilograms of pitchblende. Notice something important. So the composition of pitchblende is constant. That means the ratio of uranium to pitchblende never changes. This is exactly the law of definite composition. The concept behind this problem is very simple. Since the composition is fixed, we can use a proportion. If 84.2 grams always contains 71.4 grams of uranium, then any larger amount of pitchblende will contain uranium in the same proportion. Our plan is straightforward. First, set up the proportion. Second, solve for the unknown mass of uranium. The relationship is mass of uranium in sample divided by mass of pitchblende in sample equals mass of uranium in pitchblende divided by mass of pitchblende. Now, let's substitute the known values. Our unknown is the mass of uranium. The sample contains 102 kilograms of pitchblende. The known composition is 71.4 grams of uranium for every 84.2 grams of pitchblende. So before multiplying, we notice something. The sample is measured in kilograms, while the ratio uses grams. The units must be consistent. Therefore, we first convert 102 kilograms into grams. Now, both quantities are expressed in grams. Now, we simply multiply 102,000 times 71.4 over 84.2. And using the calculator, we obtain 86,494.06 grams. Therefore, the sample contains 86,494.06 grams of uranium. So always perform a unit check. Notice that grams of pitchblende appear both in the numerator and denominator. They cancel each other. Only grams of uranium remain. So that confirms our calculation is dimensionally correct. So far, we've seen that compounds have fixed compositions. But what happens when the same two elements form more than one compound? Do they still combine in fixed proportions? The answer is yes, but in a very interesting way. Let's now explore the law of multiple proportions. The law of multiple proportions states that if elements A and B react to form two or more compounds, the different masses of B that combine with the fixed mass of A can be expressed as a ratio of small whole numbers. That may sound complicated, so let's break it down. Suppose we keep the amount of carbon fixed. Then we observe how much oxygen combines with that fixed amount of carbon. If carbon and oxygen form different compounds, the oxygen does not combine in random amounts. Instead, it combines in simple whole number ratios such as 1:1, 2:1, 3:1, or 4:3. Nature prefers simple whole numbers. Let's use a real example. Here we compare two compounds made from same two elements, carbon monoxide and carbon dioxide. Notice that both compounds contain only carbon and oxygen. However, their compositions are different. For carbon monoxide, the composition by mass is 57.1% oxygen and 42.9% carbon. For carbon dioxide, the composition is 72.7% oxygen and 27.3% carbon. So at first glance, these numbers don't reveal any obvious pattern. So we need another approach. So the easiest way to analyze percentage composition is to imagine 100 grams of each compound. So why 100 grams? Because percentages become grams immediately. For carbon monoxide, a 100 gram sample contains 57.1 grams oxygen and 42.9 grams carbon. For carbon dioxide, 100 grams contains 72.7 grams oxygen and 27.3 grams carbon. This makes the calculation much simpler. For step 2, we compare oxygen per gram of carbon. Now, instead of comparing total masses, we compare how many grams of oxygen combined with 1 gram of carbon. For carbon monoxide, we divide 57.1 by 42.9, and that equals 1.33. And this tells us that every gram of carbon combines with 1.33 grams of oxygen. Now, let's do the same for carbon dioxide. 72.7 over 27.3 equals 2.66. So, every gram of carbon combines with 2.66 grams of oxygen. Now comes the most important part. We compare these two values. 2.66 over 1.33 is equal to 2. And the ratio becomes 2:1 because when we say two whole numbers, the denominator of that is 1. So the ratio becomes 2:1. Notice what happened. Although the percentages look complicated, the final ratio became a simple whole number. So what does this mean? It means that for the same amount of carbon, carbon dioxide contains exactly twice as much oxygen as carbon monoxide. That is why the ratio becomes 2:1. Nature did not produce 1.87, 2.43, or 3.79. It produced a clean whole number ratio. That observation strongly suggested that matter is made of tiny particles that combine one whole particle at a time. So let's look at the molecular formulas. Carbon monoxide is CO. One carbon atom combines with one oxygen atom. Carbon dioxide is CO2. One carbon atom combines with two oxygen atoms. Notice that the number of oxygen atoms doubled. That is exactly why the mass ratio becomes 2:1. So the molecular formulas themselves explain the law of multiple proportions. So the key idea is this. Whenever the same two elements form more than one compound, the mass of one element relative to the other changes only by small whole number ratios. This is exactly what we observed here. So there are three important ideas to remember. First, the law applies only when the same two elements form more than one compound. Second, the masses do not change randomly. They always change in small whole numbers. And finally, this law provided one of the strongest pieces of evidence that matter is composed of discrete particles or atoms. In other words, the law of multiple proportions became one of the key foundations of the atomic theory. So far, we've understood the concept behind the law of multiple proportions. Now, let's verify that law using another pair of compounds. Instead of carbon and oxygen, this time we will use compounds made from nitrogen and oxygen. So this example follows exactly the same procedure as the previous one. Let's read the problem. We are given the percent compositions of two compounds, nitrogen dioxide or NO2, which contains 30.45% nitrogen and 69.55% oxygen, and dinitrogen trioxide or N2O3, which contains 36.85% nitrogen and 63.15% oxygen. The question asks us to show that this data satisfy the law of multiple proportions. So our given information is simply the percentage composition of each compound. Notice that no actual masses are given, only percentages. So our first task is to convert these percentages into actual masses. Our plan consists of 4 simple steps. First, assume you have 1 gram of each compound. Second, convert the percentages into grams. And third, calculate how many grams of oxygen combined with 1 gram of nitrogen. And finally, compare the two values and express the result as a ratio of small whole numbers. So you might ask, why are we assuming 1 gram? Because percentages become very easy to interpret. If the sample is exactly 1 gram, then 69.55% simply becomes 0.6955 grams. Likewise, 30.45% becomes 0.3045 grams. And this simplifies the calculations. Let's begin with nitrogen dioxide. Since the sample weighs 1 gram, 69.55% oxygen becomes 0.6955 and 30.45% nitrogen becomes 0.345. Now let's do the same for dinitrogen trioxide. 63.15% oxygen becomes 0.6315 and 36.85% nitrogen becomes 0.3685. Now we calculate how many grams of oxygen combined with 1 gram of nitrogen. For nitrogen dioxide, we divide 0.6955 by 0.3045. And that is equal to 2.284. So, 1 gram of nitrogen combines with 2.284 grams of oxygen. Now, for dinitrogen trioxide, we divide 0.6315 over 0.3685, that is equal to 1.714. So, 1 gram of nitrogen combines with 1.714 grams of oxygen. Now we compare these two values. To obtain the simplest ratio, we divide the larger value by the smaller value. 2.284 over 1.714 equals 1.33. Now, 1.33 doesn't look like a whole number, but remember, 1.333 is the same as 4 over 3. Therefore, the ratio becomes 4 over 3. So what does this ratio mean? It means that for the same mass of nitrogen, the amount of oxygen combining with it is in the ratio 4:3. So notice that 4 and 3 are both small whole numbers. That is exactly what the law of multiple proportions predicts. So our conclusion is simple. Because the oxygen masses combine with the same mass of nitrogen in the ratio 4:3, the given data follow the law of multiple proportions. Let's compare the molecular formulas. Nitrogen dioxide is NO2, dinitrogen trioxide is N2O3. Although both compounds contain only nitrogen and oxygen, the numbers of atoms are different. That difference in atomic composition produces different mass ratios. Again, the law of multiple proportions reflects the fact that atoms combine in whole numbers, not random fractions. So this example reinforces 3 important ideas. First, different compounds can be formed from same elements. Second, the relative masses of the elements always combine in simple whole number ratios. And finally, these experimental observations became one of the strongest pieces of evidence supporting the atomic theory. So far, we've discussed 3 experimental laws that convince scientists that matter behaves in a very orderly and predictable way. But those laws naturally lead to an important question: what is matter actually made of? So scientists eventually concluded that all matter is composed of tiny particles called atoms. An atom is the smallest unit of an element that still retains the chemical properties of that element. For example, if you take a piece of pure gold and continue dividing it into smaller and smaller pieces, you will eventually reach a single gold atom, and that atom still behaves as gold. However, if you divide the atom itself, it no longer behaves as gold because you have broken it into a subatomic particles. So let's now examine the internal structure of an atom. So the slide tells us that every atom is composed of three fundamental subatomic particles: protons, neutrons, and electrons. So each particle has its own charge, mass, and location. So for proton, it is found inside the nucleus, which is the dense center of the atom. So its electrical charge is +1, written as +1. And its mass is approximately 1.0073 atomic mass units, or AMU. For simplicity, we often say that the proton has a mass of approximately 1 AMU. So one important thing to remember is that the number of protons determines the identity of an element. So for example, every hydrogen atom has exactly 1 proton, every carbon atom has 6 protons, and every oxygen atom has 8 protons. So if the number of protons changes, the element itself changes. Next is the neutron. Like the proton, the neutron is also located inside the nucleus. However, its electrical charge is 0. That means it is electrically neutral. It is neither positive nor negative. So its mass is approximately 1.0087 AMU, which is almost the same as the mass of a proton. Although neutrons have no electrical charge, they play a very important role. They help stabilize the nucleus and contribute to the total mass of the atom. Finally, we have the electron. Unlike protons and neutrons, electrons are not found inside the nucleus. So instead, they move around the nucleus in regions called electron clouds or energy levels. So the electron carries a -1 charge, written as -1. So it is only 0.000549 AMU. So compared to protons and neutrons, the electron is extremely light. In fact, its mass is about 1/1836 of a proton. That is why almost all of an atom's mass comes from the nucleus. Okay, now let's summarize the locations of the three particles. Both protons and neutrons are located inside the nucleus. And think of the nucleus as the central core of the atom. So it is extremely small, yet it contains almost all of the atom's mass. The electrons, on the other hand, occupy the space surrounding the nucleus. They move within the energy levels or electron clouds. And although the electrons occupy most of the atom's volume, they contribute very little to its mass. Now, let's answer another important question. Why doesn't every atom have an electrical charge? So the answer is shown here. An atom is electrically neutral because the number of positive protons equals the number of negative electrons. For example, suppose an atom has 6 protons, so each proton contributes +1, no? So that gives a total positive charge of +6. If the atom also has 6 electrons, each carrying -1, adding them together, 6 plus -6 equals to 0. So the positive and negative charges cancel each other, making the atom electrically neutral. So here are the key takeaways. Atoms have a central nucleus containing protons, which is positively charged, and neutrons, which is electrically neutral. Then electrons, which is negatively charged, move around the nucleus in specific energy levels or regions, and the balance of charges inside an atom results in a neutral atom. Now that we know the three particles inside an atom, the next question is, how do we identify one element from another? So scientists use two important quantities, the atomic number and the mass number. So let's learn how these numbers allows us to identify every element in the periodic table and determine the number of neutrons in an atom. The atomic number of an element equals the number of protons in the nucleus of each of its atoms. So all atoms of a particular element have the same atomic number, and each element has a different atomic number from that of any other element. So again, remember, atomic number equals the number of protons in the nucleus. It identifies the element, and every atomic number is unique for each element. So atomic number is represented by letter Z. So for example, for carbon, since it has 6 protons in the nucleus, therefore, the atomic number is equal to 6. For the mass number, it is the total number of protons and neutrons in the nucleus of an atom. So each proton and each neutron contributes 1 unit to the mass number. So the mass number is the sum of protons and neutrons. So the number of neutrons equals the mass number minus the atomic number. So neutrons is represented by N, A is represented by the mass number, and Z is the atomic number equal to the number of protons. So, for example, if an atom has a mass number equal to 14, it can be found in your periodic table, and the atomic number is 6, also found in your periodic table. Therefore, the number of neutrons is equal to 14 minus 6, or equal to 8. So, the atomic number, again, identifies the element by the number of protons, and the mass number tells us the total number of protons and neutrons in the nucleus. Now that we've learned that every element is identified by its atomic number, and we've also learned how to calculate the mass number, now the next question is, how do chemists write all of this information in a simple and standardized way? So the answer is through the atomic symbol. So the nuclear mass number and charge are often written with the atomic symbol or element symbol. So every element has a symbol based on its English, Latin, or Greek name, such as C for carbon, O for oxygen, S for sulfur, and Na for sodium, from the Latin word natrium. So let's now understand how to read the complete atomic notation. So at the center is the chemical symbol represented by X. The upper left number represented by A is the mass number. And remember that this is the total number of protons plus neutrons. The lower left number represented by Z is the atomic number, which is simply the number of protons. So finally, if the atom has gained or lost electrons, its electrical charge is written at the upper right as Q. So if there is no charge shown, we assume that the atom is electrically neutral. So far, we've assumed that every atom of an element has exactly the same mass. But is that always true? The answer is no. So that brings us to the next concept, isotopes. So all atoms of an element are identical in atomic number but not in mass number. So isotopes of an element are atoms that have different numbers of neutrons and therefore different mass numbers. For example, carbon has many isotopes and is usually written as carbon-13 with a superscript as its mass number. So examples of isotopes of carbon, we have carbon-12, which is the most common, carbon-13, and carbon-14. So if we look at this table, for carbon-12, carbon-13, and carbon-14, the number of protons is just the same. It's all equal to 6. However, for the neutrons, they have different numbers because they have different mass number. So for carbon-12, the neutrons is 6. For carbon-13, the neutrons is 7. For carbon-14, the neutrons is 8. Therefore, for isotopes, they differ only in the number of neutrons. That is why they have different mass number, but the number of protons stays the same. So isotopes may have different stability and abundance. So this is an important clarification. So some may think that changing the number of neutrons creates a new element. So again, that is not true. Changing the number of neutrons only creates a different isotope of the same element. So to create a completely different element, you would have to change the number of protons. Now that we know how atoms are represented and understand why elements can have different isotopes, the next question becomes, how are all of these elements organized so scientists can study them more easily? So to answer that, we'll move on to one of the greatest achievements in chemistry, the periodic table of elements. But before we begin discussing the periodic table, I'd like to share a fascinating story. So imagine that you're given more than 60 puzzle pieces but no picture of what the finished puzzle should look like. So your task is to arrange those pieces into a meaningful pattern. So that was exactly the challenge scientists faced in the 1860s. At that time, only about 63 elements had been discovered. Scientists knew some of their properties, but they had no systematic way of organizing them. It was like having a box of puzzle pieces without knowing how they fit together. One Russian chemist, Dmitry Mendeleev, believed there had to be an underlying pattern. Legend has it that he wrote the name and properties of each known element on individual cards, much like playing cards. He spent hours arranging and rearranging them, looking for relationships among their properties. Eventually, he noticed something remarkable. When he arranged the elements according to increasing atomic mass, certain chemical properties repeated at regular intervals. This repeating pattern is why we use the term periodic. But here's the most amazing part of the story. Mendeleev discovered that some places in his table were empty. Instead of forcing the table to fit the known elements, he boldly left blank spaces, predicting that new elements would eventually be discovered to fill those gaps. Even more impressive, he predicted the properties of those unknown elements, their approximate atomic masses, densities, melting points, and even how they would react chemically. So years later, scientists discovered elements such as gallium, scandium, and germanium, and their measured properties closely match Mendeleev's predictions. So imagine predicting the characteristics of something that no one had ever seen. That achievement transformed the periodic table from a simple list of elements into one of the most powerful predictive tools in science. So the next question is, what makes the periodic table such a powerful tool? Is it simply because it lists all the elements? No, not at all. The periodic table is a tabular arrangement of all known chemical elements. The elements are organized primarily according to their atomic number. As the atomic number increases from left to right and from top to bottom, patterns begin to appear. Elements with similar electron configurations and similar chemical properties naturally fall into the same columns. That is why the table is called the periodic table, because many chemical properties repeated periodically. So let's first look at the horizontal rows. These rows are called periods. There are 7 periods in the modern periodic table. Periods are simply numbered from 1 to 7, and every element in the same horizontal row belongs to the same period. As we move from left to right across a period, the atomic number increases 1 proton at a time. So periods also tells us something important about atomic structure. Elements in the same period have the same number of occupied electron energy levels. For example, all elements in period 3 have 3 occupied energy levels, so periods are closely related to the arrangement of electrons. Now, let's look at the vertical columns, and these are called groups or families. Notice that they extend from the top of the table down to the bottom. Elements in the same group have similar chemical properties. Why? Because they have similar arrangements of electrons in their outermost energy level, also called valence electrons. So notice how the table is arranged. The numbers at the top identify the different groups, and the numbers along the left side identify the periods. Every box in the table represents one chemical element, and inside each box, you would normally find information such as the atomic number, chemical symbol, element name, and atomic mass. You may also notice 2 separate rows placed below the main table. These are called the lanthanides and actinides. Technically, they belong inside the main table, but if they were inserted there, the periodic table would become much wider and difficult to fit on a page. For convenience, they are displayed separately at the bottom. Now that we know how the periodic table is organized into periods and groups, let's become familiar with some of its most important families of elements, such as the alkali metals, alkaline earth metals, halogens, noble gases, and transition metals. These families will help us understand why different elements behave so differently in chemical reactions. The first family is the alkali metals. These elements belong to group 1A or group 1 with the exception of hydrogen. Examples include lithium, sodium, potassium, rubidium, cesium, and francium. So these metals are known for being highly reactive, especially when they come into contact with water. For example, sodium reacts vigorously with water, producing heat and hydrogen gas. The second family is the alkaline earth metals found in group 2A or group 2. Examples include magnesium and calcium, and these metals are also reactive but not as reactive as the alkali metals. The third family is the coinage metals located in group 1B or group 11. This family includes copper, silver, and gold. They are called coinage metals because they have historically been used to make coins, and these metals are excellent conductors of electricity and heat. Next are the halogens located in group 7A or group 17. Examples include fluorine, chlorine, bromine, and iodine. So halogens are very reactive nonmetals. They readily combine with metals to form salt. So for example, table salt or sodium chloride is formed when sodium reacts with chlorine. And the final family shown here is the noble gases found in group 18. Examples include helium, neon, argon, krypton, xenon, and radon. So, unlike the alkali metals and halogens, the noble gases are very stable. They rarely react with other elements because their outer electron shells are already complete. So far, we have learned that the periodic table is organized into periods, groups, and families. Now, let's take one step back and look at the overall structure of the periodic table. So instead of focusing on individual groups, we can divide the table into three major structural regions, or what we call macro blocks. So let's begin with region 1, the main group elements. Notice that these elements are found on both sides of the periodic table. On the left side, we have group 1 and 2, while on the right side, we have group 13 through 18. So although they appear separated, they actually belong to the same category called the main group elements. So they are called the main group because they include the elements we encounter most often in everyday life. For example, hydrogen, carbon, nitrogen, oxygen, sodium, magnesium, aluminum, chlorine, and the noble gases. These elements form the majority of the compounds we use daily. The second region is the transition elements. This is the large block located in the center of the periodic table. It includes what we commonly call the transition metals. Transition elements are generally strong, hard, dense, good conductors of heat and electricity, and capable of forming many different compounds. Some familiar transition metals include iron, copper, nickel, chromium, titanium, zinc, and silver. The third region is called the inner transition elements. These are the two rows usually placed below the main table. The first row is called the lanthanides, and many lanthanides are used in advanced technologies. The second row is called the actinides. One important fact to remember is that all actinides are radioactive. Now let's look at another important way of classifying the elements. This classification is based on a special boundary called the stepped line or the zigzag staircase. So this zigzag boundary is known as the step line. Think of it as a dividing line that separates elements according to their physical and chemical properties. It doesn't divide the periodic table perfectly, but it provides an excellent guide for classifying the elements into three major categories. Let's begin with the largest region, the metals. Notice that almost all elements to the left of the stepped line are metals. In fact, metals make up nearly 80% of all known elements, making them the dominant class of materials. On the opposite side of the stepped line are the nonmetals. These are mostly located on the upper right side of the periodic table. One exception is hydrogen. So although hydrogen is located on the far left, it is not a metal. Because of its chemical behavior, it is classified as a nonmetal. Now let's focus on the elements located directly along the stepped line. So these are called the metalloids. Metalloids are unique because they possess properties of both metals and nonmetals. Sometimes they behave like metals, sometimes they behave like nonmetals, and their properties fall somewhere in between. So when you look at the periodic table, remember the simple rule: left of the step line, mostly metals; right of the step line, mostly nonmetals; and along the step line, metalloids. With that, we have reached the end of today's lesson. Thank you for your attention. Have a wonderful day, everyone, and God bless.